Okay, why is this important? Well, not only mortality risk is strongly associated with biological age, but nearly every significant functional decline and disease of aging is strongly associated with biological age. This is important, right? Because I think one of the things we've learned from studies in laboratory animals is it really doesn't seem like there's a point at which it's too late to have an impact on your biological aging rate. My name is Matt Kaeberlein, and welcome to the OptiSpan YouTube channel. Hey everyone, welcome to the OptiSpan podcast. In this third episode on the science of longevity, we're going to dive into this complicated topic of biological aging. So if you've ever wondered what people are talking about when they're talking about biological age or biological age clocks, this episode is for you. So I want to start by just putting out a few definitions just to make sure everybody's on the same page. And the first one is really easy. The first definition is for chronological age, which is just the length of time that you've been alive, the number of birthdays that you've had. And I want to differentiate chronological age from biological age. Biological age, I'm going to define as how old your cells and tissues are based on their physiological function. And as we will talk about, chronological age and biological age don't have to equal each other. In fact, most of the time they won't. And then the final thing I want to define is what we mean by biological aging. And there are really many, many different ways that we can try to define biological aging. We do it at the molecular level. I'm going to use sort of a more higher level definition today, which is the loss of homeostasis over time as the result of both internal and external processes. And that word homeostasis really just refers to the ability of complex systems to return to normal function or a normal state after a perturbation. And I'm sure you can appreciate that our bodies, our cells, our tissues, our organs are constantly being exposed to stressors that kind of move them out of their optimal functional state or their normal functional state. And when we're young, our bodies are quite able to restore function when they've been perturbed. But as we get older, we lose that resilience, we lose that ability to restore homeostasis. And this is seen in every biological system where aging has been studied. So I think it's a pretty good universal definition of biological aging. Okay, so to kind of illustrate these concepts and the idea of the difference between chronological age and biological age, I want to start with an analogy for something that we're all sort of familiar with, automobiles. So if we think about two people, we'll just call them Gary and Tom, and they both purchased exactly the same make and model of car in the year 2018. Okay, so Tom is a very responsible driver. He always uses the highest grade of gasoline. He's vigilant about doing preventative maintenance according to the manufacturer's recommendations. He's never been in a single accident. And Gary's sort of the opposite. Gary is an extremely aggressive driver. He always buys the lowest grade of gasoline because it's cheaper. He ignores the check engine light and oil change reminders, doesn't do any preventative maintenance until something breaks. And he's been in 2 significant collisions and a whole bunch of fender benders. And so I'm sure if you just imagine in your mind what these 2 cars are going to look like 5 years later, they're going to look very different, right? And so I think this is again, a useful sort of analogy for what we think about with biological aging. This, of course, is a mechanical aging process, but the idea that we take care of our bodies in different ways, and that can impact the rate at which our bodies are showing wear and tear. And we can take the analogy one step further and kind of look at this through the lens of lifestyle factors, right? So Tom from the automobile story and Tom the goat, right, may have some things in common where things like nutrition and exercise and preventative health care and limiting risky behaviors, and of course genetics are going to play a role too. All of those are going to influence our biological aging rate, much like the way that you take care of your car will influence its mechanical aging rate. Okay, so hopefully that's a useful analogy. And I want to now get into 3 concepts about biological age, and that's what we'll spend most of the rest of the time doing today. So the first concept is that the variation in biological aging rate is really what determines the difference between chronological age and biological age. And we'll show some graphics to illustrate that in a minute. The second is that biological aging rate can vary both within species, and what I mean by that are individuals of the same species, but they can also vary quite dramatically when we look across species. And then finally, health and mortality risk are both related to, but neither are equivalent to biological age. And this connection between biological age, rate of biological aging, and health is why this is such an important topic to study. Okay, so the first one, variation in biological aging rate determines the difference between chronological age and biological age. And I'm going to start by getting a little bit mathematical, but I promise this will be pretty basic. So if we just think about a graph where we have chronological age, again, number of birthdays, length of time that you've been alive on the x-axis, and we plot that with biological age on the y-axis. And if you look across the entire population of people, or if we were doing this in mice, the entire population of mice, very large populations, on average, biological age is going to equal chronological age. Now, in this particular case, I've sort of arbitrarily said that when somebody reaches the biological age of 85, that's the point at which they die, right? So mortality would be 100% in this case at the biological age of 85. That's what the red X represents. Now, of course, that's not true in the real world. There's all sorts of probabilistic stuff that comes into play. But for this simple example, let's just assume that when somebody reaches a biological age of 85, their mortality risk reaches 100%, and it's 0 at every biological age less than 85. And it's really biological age that's going to determine mortality risk. So if we now think about somebody who maybe has a biological aging rate that's 25% higher than that population average, so this is now an individual, and we plot their aging trajectory on the same graph, you can see that the slope of this line is steeper, right? They're aging biologically more rapidly than they're aging chronologically. And so at any point on this line, the red line, if you look at a biological age, let's say 50, biological age of 50 in this person, they're going to have a chronological age of only about 45. So this is somebody who's aging more rapidly. They're accelerated aging. Because they are showing this accelerated aging rate throughout their entire life, they're going to reach a biological age of 85 at a chronological age of less than 85. So they're going to die somewhere in their mid-70s. Now, we can also take the opposite case where somebody is aging about 25% more slowly than the population average. And in this case, the slope is less. And at every biological age, their chronological age is actually going to be greater than their biological age. And because this person is aging biologically more slowly, they're actually not going to reach a biological age of 85 until they're well over 100. So this would be somebody who we would call a centenarian, right? Meaning they lived longer than 100 years old. Okay, so this hopefully illustrates, the fact that some people are going to age biologically more rapidly than the population average. Some people are going to age biologically more slowly than the population average, and that will have an impact on their predicted chronological age because mortality rate goes up exponentially with biological age. Okay, now one thing this graphic doesn't represent is that, of course, in reality, our biological aging rate can change. In fact, it's probably changing over very short timescales even, right? So lifestyle modifications, for example, can have a pretty big impact on biological aging rate. And so you could go from aging more rapidly than average to aging more slowly than average. And if we consider a hypothetical 40-year-old person who maybe was sedentary and ate a low-quality diet and drank a lot of alcohol, until they reached the age of 40. And then they decided, oh man, I better get my act together or I'm going to be headed for an early grave. So they cut back on alcohol, they started eating a healthy diet and started exercising regularly. They could change their rate of biological aging in midlife. And what this graphic is showing is the impact in the green line of that kind of a change in biological aging rate due to lifestyle modifications. And so somebody who was destined to die in their mid-70s might actually, by modifying their rate of biological aging, live to be 90 years old or even greater. So this is important, right? Because I think one of the things we've learned from studies in laboratory animals is it really doesn't seem like there's a point at which it's too late to have an impact on your biological aging rate, unless you've developed a specific age-related pathology that has sort of gotten beyond biological aging. So as an example, metastatic cancer, where it's spread, it's not obvious that if you were to modulate your rate of biological aging, you could do anything about the metastatic cancer at that point. So the pathology of the disease has sort of outpaced biological aging. But in the absence of that, it seems pretty clear, again, at least from preclinical studies in the laboratory, you can have big impacts on biological aging rate very late in life. And I think the same thing is almost certainly true in people. We all know of people who have waited until they are late in life to make significant changes in their lifestyle habits. You can still grow muscle, you can still improve cardiovascular function, you can do all sorts of positive things to your health late in life that are probably having an impact on your health because they're directly modulating biological aging. So that's what we are all about at OptiSpan, is really about helping people to achieve this slower rate of biological aging and recover their lost decades. Okay, why is this important? Well, one of the reasons why it's important is because not only mortality risk is strongly associated with biological age, but nearly every significant functional decline and disease of aging is strongly associated with biological age. And so if we can impact the rate of biological aging, we have the potential to impact many, maybe all of these functional declines and diseases simultaneously. And for a deeper dive on that, I would refer you to our episode on understanding aging and disease and how they're related. Okay, so the second concept about biological age that I want to talk about today is how biological aging rate can vary dramatically both within and between species. And so the within part is kind of obvious. Again, that's the example that we went through just a second ago. We also all know from our own lives, we can identify people who seem to be aging more rapidly or more slowly. I think dogs are a really interesting way to illustrate both of these concepts, both the within species variation in biological aging rate and, of course, the cross-species variation rate in biological aging. So within species, if we think about dogs, we all probably recognize that big dogs age biologically faster than small dogs do. Big dogs have a shorter life expectancy, and they seem to develop diseases of aging at a much earlier chronological age compared to small dogs. And so this is very consistent with the idea that big dogs have a higher biological aging rate than small dogs do. Or if we were to plot small, medium, and large sized dogs on that same graph that I showed before, the big dogs would have the steepest slope and the small dogs would have the shallowest slope. So within the same species, dogs are all one species, right? They can all mate with each other. Within the same species, there can be quite large variation in biological aging rate. Of course, the passage of chronological time is the same. Now, there was this very interesting study that was published by the Ostrander and Eidecker labs a couple of years ago, where they actually looked at the comparison between one metric of biological aging between dogs and humans. And in this particular case, they used epigenetic age. And it's epigenetic age that is powering a lot of these commercially available biological aging clocks. We can talk more about that later. But using this one metric of biological age, what they found was really interesting, that when you compare dogs to humans, this difference in the rate of epigenetic aging was much steeper at young age in the dogs than at old age. In other words, when the dogs were, say, 6 months or 1 year old, they were maybe aging, epigenetically aging about 15 times faster than people. But when dogs got older and were sexually mature, that slowed down quite a bit towards maybe where out towards the end of their life, they were only aging epigenetically about 2.5 times faster than people. So not only can biological aging rate vary quite dramatically between species, but it can actually vary quite dramatically throughout the life course in different species. And that's something that's really just starting to be studied. The other thing that I think is so fascinating is if we look across the animal kingdom, we can see that nature has really figured out how to vary biological aging rate by many, many orders of magnitude, certainly more than 100-fold, probably even more than 1,000-fold if you start to look at some of the really, really short-lived species. And so what this tells us is that there's a lot of opportunities to modulate biological aging rate. And by studying some of these outlier species, it gives us an opportunity to really understand what are the biological mechanisms that can have these very, very large impacts on biological aging rate. The pink wrinkly guy here is a really interesting example. That's the naked mole rat. And genetically, naked mole rats are pretty close to other rodents, to mice and rats. Mice and rats, if you put them in a protected environment like the laboratory, will grow old, develop the diseases of aging, and die in about 3 years. Naked mole rats, in a similar sort of protected environment, can live 30, 40 years. So there's about a 10-fold difference in biological aging rate just between these two pretty genetically close species. And so again, this gives us real opportunities to understand what are some of the major determinants of biological aging rate that can have such a large effect. Okay, so then the last topic that I want to talk about today is this idea that health and mortality risk are both strongly related to, but neither are equivalent to biological age. So why this confuses people is because mortality risk, which is again just your risk of dying, increases exponentially as we get older. And health generally declines quite dramatically as we get older. And in particular, I would argue that biological age is the largest determinant of mortality risk and poor health for most people. The important point here, and I guess it's a little bit of nuance, but the important point here is it's not the only determinant. So I'm sure if you thought about it for a few minutes, you could come up with many ways that you could reduce your lifespan or dramatically negatively impact your health that would have nothing to do with biological aging. So there are many ways to impact mortality and health that are not related to biological aging or biological aging rate. The reason why I think this is important is because these so-called biological age clocks are generally trained on either mortality or on fairly simplistic measures of health. So they're not actually measuring biological age. That's really the take-home message, is that none of these quote-unquote biological age clocks are actually directly measuring biological aging. They are measuring things that are correlated with biological aging. And so when somebody's trying to tell you that they can measure biological age, it's just important to appreciate they can't really. Okay, so what about reversing aging? There's a lot of talk these days, particularly in the media and by some influencers, about this idea of reversing aging. So let's think about what that would actually look like on the graph that I showed earlier of chronological age versus biological age. If somebody actually had a way to reverse biological aging, what you would see is that up until the point that a person used this intervention, maybe it's a drug, maybe it's a gene therapy, maybe it's something else, up until the point where they used this intervention to reverse aging, they would age normally. Their biological age would more or less track with their chronological age. Then they take this intervention, and over presumably a short period of time, let's say a year, their biological age would drop quite dramatically. In this particular graphic, it's a 20-year drop in biological age over a 1-year period of chronological age. And then when they stopped the intervention, they would immediately go back to their old rate of biological aging and be parallel to the line of the population or people who had never taken the intervention. And of course, you could imagine all sorts of variation on this. Maybe you repeat the age reversal intervention at 20-year periods, whatever. The point here is that we don't have anything that actually appears to do this. We don't have any interventions that actually seem to make an old person or even an old animal, this has never been done in the laboratory, biologically younger again, where all of the age-related traits are in fact reversed or reduced by some significant amount of biological age. So I would argue pretty strongly that reversing aging is not yet possible. Maybe it will be someday. I don't think it's going to happen anytime soon, but certainly I think it's plausible that eventually we could come up with a way to reverse biological aging. What we can do is reverse a subset of phenotypes or traits of aging, things that change with age. Some of them can be reversed. And again, this should be pretty obvious. If you think about cosmetic changes, we've known for decades how to reverse cosmetic changes, some of them that go along with aging. Just think about hair color. You could take black hair color and put it on your gray hair. If your hair was black when you were younger, you have reversed that aging trait. Did that reverse biological aging? No, of course not. It reversed the change in your hair color with age. We can do that with things that are maybe a little bit more physiologically relevant for biological age, though, like body composition, right? Of course, we all know it's possible to gain lean mass or lose adipose, lose fat mass. Age-related changes in body composition can be reversed. Did that reverse your entire biological aging? No, of course it didn't. We can reverse functional aspects of fitness, VO2 max. We can reverse age-related changes in vaccine response. And we can reverse some molecular changes of aging. So in the laboratory, people have shown we can reverse hyperactivation of mTOR with drugs like rapamycin. We can reverse age-related changes in some tissue in metabolites like NAD. We can reverse some age-related epigenetic changes. We can reverse age-related hormonal changes in laboratory animals and in people. That's what hormone replacement therapy are. None of these things are reversing all of biological aging, which is why I, again, pretty strongly say that nobody has reversed biological aging as an entire process. How will we know? I think this is a more interesting question. How will we know when biological aging has really been reversed? And I would say kind of the gold standard is you got to make an old animal young again. When I see that, I'm going to believe that you've reversed biological aging. I kind of think we'll know it when we see it. It ought to be pretty darn obvious. Now, again, some people are trying to claim they've reversed aging. I would just say they haven't. I would further suggest that the burden of proof is really on them to prove they can make an old animal young again. Remarkable claims require remarkable evidence. So my advice would be, don't believe it until you see it. Okay, so the take home here is that, having said all that, improving health and reducing mortality by targeting biological aging can, in fact, reverse some of the functional declines that go along with aging. And that's really important. Recovering our lost decades is important. Improving quality of life is important. I just don't want to minimize the impact of what we can do today by deceiving people with science fiction, which is why I push back against the idea that people have reversed aging. Okay, so let's finish up by just reviewing the key concepts that we talked about today. First of all, variation in biological aging rate determines the difference between chronological age and biological age. Biological aging rate can vary dramatically, both within species at the individual level and across species. And in fact, it varies much more dramatically when we look across the animal kingdom. Health and mortality risk are both related to, but neither are equivalent to, biological age. And again, the important point here is that the biological age tests, which I don't even like that term, the quote unquote biological age tests don't actually measure biological age directly. And then finally, improving health and reducing mortality risk by targeting biological aging, I believe, is possible today. And I think that's really important. So as always, thank you for watching. If you have any comments or questions, please put them in the comment section below. If you like this content, I'd encourage you to subscribe to the channel, and I'll see you next time on the OptiSpan podcast.